In the first few decades of the 1900s, scientists struggled to explain recently observed phenomena, and as a result, developed a totally new theory, quantum mechanics. This new theory explained weird behavior, such as particles acting like waves, or atoms emitting light at discrete wavelengths. When someone talks about a quantum system, that means that the laws of quantum mechanics predict how the system behaves. For example, think about a bunch of atoms in a crystal. Each atom has something called spin, which can be measured to be either up or down. We'll call this our spin system. The Hamiltonian describes the energy associated with a particular state. If an atom is spin up in a magnetic field, it will have a different energy than if it's spin down. It turns out that how things change in time depend on the Hamiltonian. For all quantum systems, like our collection of spins, there's a natural Hamiltonian, which describes the dynamics of the system if we didn't do anything. But we can also engineer totally different Hamiltonians that lead to different dynamics. We can turn off interactions we don't want, or create new interactions to study. In a spin system, the engineering part is done by applying a series of magnetic field pulses, which we call a pulse sequence. With an engineered Hamiltonian, we can build incredibly sensitive quantum sensors or implement a quantum simulator. In the 1960s, some scientists came up with a mathematical framework called average Hamiltonian theory, which was used to construct the first pulse sequences for nuclear magnetic resonance experiments. This framework is still used today to design new pulse sequences. However, it only gives an approximation for how the quantum system behaves, which differs from what actually happens in experiments. I'm trying to see whether Hamiltonian engineering can be approached a totally different way, using reinforcement learning. In reinforcement learning, an agent interacts with an environment to get rewards, and over time learns what actions to perform on the environment to maximize the rewards it gets. For my research, the environment is a spin system, the actions are magnetic field pulses, and the rewards are how close the actual Hamiltonian is to the target Hamiltonian. There are several potential advantages to reinforcement learning over current methods. The approximations that average Hamiltonian theory uses are not made with the reinforcement learning approach, which means a more accurate representation of the physical system. Also, it's straightforward to include real-world constraints and let the agent learn how to behave within those constraints.